As we continue with PhysioEx 10 videos, we have exercise 5, activity 5, studying the effect of blood vessel radius on pump activity. Okay, so this one's a little bit more, has a few more moving parts than what we saw with the first 4 activities in exercise 5. Okay, we're going to look at systole and diastole, change in blood vessel radius affecting flow rate, change in blood vessel radius affecting heart rate. Okay. And so a couple of, a little bit of background real quick. Again, I know you will read this or have read this. You know or will know some of these terms. Diastole is the relaxation of the heart. Systole is the contraction of the heart. We've seen these terms, systolic and diastolic, for blood pressure. We know the systolic number is the top number, 120, for example, over 80. Okay, so systole and diastole have to do with contraction and relaxation. So as the heart is filling, as the ventricles are filling, we're going to have a volume in the ventricles at the end of filling. So just before the contraction, we're going to have what's called end diastolic volume. So again, diastole has to do with the filling and relaxation, and we have an end diastolic volume right before the ventricles contract. So basically, how much blood is in the ventricles. Okay. And then the end systolic volume is the remaining blood in the ventricle after a contraction or a systole type of event. So we're going to look at that. How much blood is in the heart or in the ventricles before it pumps, how much blood after it pumps. Okay. And that amount, the difference between the two, is called the stroke volume. So in other words, how much blood was ejected from the heart. All right. So cardiac output is a fancy way of saying blood flow. So flow and cardiac output are the same thing. So how do we determine cardiac output or blood flow? And again, we look at cardiac output in terms of milliliters per minute. Okay, to determine blood flow or cardiac output, we're going to multiply heart rate, how many beats per minute, times stroke volume, how much blood is ejected every time a ventricle contracts. Okay. So we multiply beats per minute times the volume ejected per contraction. And that's going to give us how much blood, milliliters per minute, the heart is pumping. All right. Also known as blood flow. We know that blood pressure equals flow or cardiac output times resistance. Okay, so R has to do with resistance. So in resistance, we'll be looking at, or we did look at, radius or diameter, how big around is the vessel, can determine resistance. So anyhow, so blood pressure equals cardiac output or blood flow times resistance. All right, so we can take out flow or cardiac output and insert heart rate and stroke volume. So that's what's going on here. I know whenever math equations and letters and numbers start getting thrown around, folks get a little bit antsy. So all we've done is taken heart rate times stroke volume, which gives us blood flow, And we've taken out flow and the word flow and replaced it with what flow is: heart rate and stroke volume. So that's what we have down here. We could even put a parenthesis there and a parenthesis there just to really tie it all together. But I think you can see that we've simply replaced cardiac output with the word flow. They're the same thing. And now we've replaced flow with the equation to determine cardiac output. So we have heart rate times stroke volume times resistance giving us blood pressure. So if any of these go up or go down, then blood pressure will go up or go down. So if stroke volume and resistance stay the same and heart rate goes up, we're going to see an increase in blood pressure. So generally, we try to maintain constancy with blood pressure of 120/80. Generally, too, we're going to see stroke volume. The heart tries to generally ejects the same amount of blood for every beat. So stroke volume generally will remain constant. So if we alter either of these, so if we increase resistance, but this has to stay constant, we would have to decrease heart rate. Vice versa, if we decrease resistance, we'd have to increase heart rate to maintain normal blood pressure. Because if SV, stroke volume, and blood pressure are constant, and these two fluctuate, then when one of these goes up, the other one has to go down in order to maintain constancy. Okay, so that's basically what this experiment is, or activity is going to do. We're going to keep blood pressure and stroke volume at constant. We're going to alter for the resistance portion. We could alter viscosity, we can alter diameter or radius, we can alter the length. All of these things are possible for resistance. For this particular one, we're going to keep it to radius or diameter. So the size of the lumen, or the size of the blood vessel internally. Okay, the radius or the diameter. All right, so that's what we're going to alter. Okay, so if we decrease if we increase diameter, we decrease resistance. So what we're going to be doing is increasing the diameter. That's going to cause a decrease in the resistance. So if the tube is bigger around, there's less resistance. So we're going to see a decrease in resistance. So to compensate for less resistance, we're going to see the heart rate increase. Okay, so keep an eye on that. We're going to have a lot of moving parts, or what appear to be a lot of moving parts. We're going to have a left beaker that's going to have blood in it coming from the lungs. So there's going to be a small amount of pressure, around 40 millimeters of mercury of pressure, that's pushing or sending blood from the lungs back to the left side of the heart. So the tube coming from that left beaker, the left flow tube, would simulate the pulmonary veins, because remember, veins always go towards the heart. So the pulmonary veins are going to be bringing oxygenated blood from the lungs to the heart, or from the left beaker through the flow tube into the heart. And for this, we're going to have a pump that's simulating the left ventricle. So we bypass the atrium, and we're just going to put that blood right from the pulmonary veins right into the left ventricle. Of course, in reality, we go through the left atrium, then the left ventricle. Okay, so anyhow, there is a valve right before we enter into the pump that does represent the bicuspid or mitral valve. So this flow tube kind of represents the pulmonary veins into the left atrium, and then we get this little valve that opens up into the pump, which is going to simulate the left ventricle. And then there's a valve, of course, that's going to, as we leave the left ventricle, the aortic valve is going to, we're going to see that as well. And another tube then simulating the aorta leaving that pump. Okay, and then we're going to get to a right beaker, and that's going to simulate then the systemic circuit, or blood going out to the body. So let's take a look at all of this. There are a couple of questions for you to go through on your own. Okay. We're going to get right to it because, again, there are a lot of moving parts. Once it gets going and we see what's going on, it flows pretty smoothly. So, all right, so let's take a look at what's going on here. We have this left beaker representing blood in the lungs. And as blood leaves the lungs into the pulmonary vein and then the left atrium, we're going to get our bicuspid or mitral valve dumping into the left ventricle. Okay, and notice the pump pressure in the left ventricle is going to be set at 120 millimeters of mercury. Okay, that's that systolic number that we see when we take a blood pressure measurement, or that we should see. Okay, so as we leave the left ventricle, we see the aortic valve here. And then this tube represents then the aorta and all of the subsequent arteries that branch off the aorta and lead us out into the systemic blood circulation system. So this represents the body, and this represents the lungs. So, so anyhow, that's what we have going on here. And notice too the pressure constant from the lungs to the left side of the heart. We don't need a lot of pressure. We're not going very far. It is venous blood. So generally we do see lower pressure with venous blood anyway. So 40 millimeters of mercury. So that's going to be constant. The volume contained is also going to be constant as we start pumping at 5,000. Now, we come down and we look at some of these other numbers. We've got the pump volume. So now we're looking at this pump volume at the start of 120 milliliters. Now, remember, that could also be called the end diastolic volume. So this is the amount that's in the left ventricle while it's filling, and once it's done filling, we call that the end diastolic volume. So in other words, the pump is relaxed, or the ventricles are relaxed, and they're receiving blood. Okay, so that end diastolic volume is 120 mLs. Okay. And then we're going to see the pump. Okay, so this little 120 millimeters of mercury of pressure is going to push down. This valve's going to open, and we're going to see blood going into the aorta and heading over to the systemic circuit, or to the body. After each pump, we're going to have, so this 120 milliliters is not going to leave the heart. It's not going to empty entirely. We're going to have an end volume, what we'd call an end systolic volume of 50. So after the contraction, we have a volume left over of 50. Okay, so we subtract 120. What did we have at the beginning? The end diastolic volume. What did we have at the end after the contraction? We had 50 milliliters, the end systolic volume. That's going to give us our stroke volume, how much blood was ejected, pardon me, how much blood was ejected when the ventricle contracted. All right, so 70 milliliters as our stroke volume. We're going to leave that as a constant as well. All right, so pressure, stroke volume, going to remain constant. The other thing we're going to leave constant is the left flow tube radius. So that pulmonary vein heading from the lungs to the left atrium is going to be kept at 3.5 millimeters. All right, so 3.5 coming into the heart, and then the right tube is going to symbolize the um, aorta, and we have that set initially at 3 millimeters. Okay, so 3.5 coming in, 3.0 going out. So this is the number that we're manipulating, going back to our original equation of blood pressure being a constant, okay, and then stroke volume being constant. Okay, so heart rate and resistance are the two items that are going to be altered. What we're going to alter is the amount of resistance. So we're going to start with the radius of 3. We're going to increase this radius. So this tube will get larger. And as you'll recall, if we increase radius, we decrease resistance. So as resistance goes down, we would see blood pressure potentially go down as well. So what we need to do to maintain blood pressure is we need to increase either stroke volume or increase heart rate. So remember, we're leaving stroke volume where it is, so heart rate is going to go up. So that's what we're going to look for. If heart rate goes up, so what happens to flow or cardiac output? If heart rate goes up, stroke volume stays the same, cardiac output or blood flow is going to go up. So we should see as well, as we increase radius leaving the heart, we decrease resistance. We're going to see then an increase in heart rate, thus an increase in cardiac output, so, or blood flow. So anyway, that's what we're going to keep an eye on. We're going to do one single pump just to simulate kind of what we're doing. We got one pump. Remember, stroke volume is 70, so we would expect there to be 70 milliliters over in this beaker. So if I continue to keep that going, then, after 60 seconds, we would see a cardiac output or blood flow of 40 on the magnitude of 4,200 milliliters per minute. So anyhow, before we can move on, for this particular experiment, we have to do a few things before it'll let us go. I know some of these we can click through pretty quickly. Let's see, volume remaining in the pump. And okay, so now it's going to have us do 10 strokes. Okay, so auto pump. So we should get to, we had 70 in there already, so we added 10 more strokes, 70 per stroke, so that's 700 plus the original 70. Gave us that 770 milliliters. So anyhow, if we measure that out and do a little bit of multiplication, we're going to get a flow rate of 6,607 milliliters per minute. Now, with the right, so this is kind of our baseline. We're going to start with a flow tube radius of the aorta at 3.0 millimeters. So again, we kept stroke volume constant. We have the left radius at 3.5, which will keep constant throughout, and then that right starting radius of 3.0. Pressure in the left we saw was 40. Okay, 40 coming here. And then we're going to look at the pressure difference, 120 over 80. We can get the difference in pressure of systolic and diastolic, which is going to give us 40, which is an important number clinically. If someone has a blood pressure of 130 over 90 on the surface, it may seem a little bit high, which it is. But more importantly, we do still see a 40 millimeter of mercury difference between systolic and diastolic pressures. So that difference in pressure from systolic to diastolic is going to be something that we look at in the clinic beyond just are these two numbers off. We also look at the distance between the two numbers. So anyway, the pressure difference from ventricles contracting and then out to the arteries or out to the body system shows us a pressure difference of 40. Okay, so remember these are going to be maintained. We're maintaining pressure throughout. We're maintaining stroke volume throughout. What we're doing is getting a baseline of 3 millimeters radius. That's going to give us a stroke per minute or a heart rate of 94.4. Okay. So we can determine flow, which is also, remember, cardiac output. Okay? Flow and cardiac output are the same thing. And we know that cardiac output, we can find that number by multiplying stroke volume times heart rate. So stroke volume is 70, heart rate is 94.4. We multiply those two numbers, we're going to get a cardiac output or flow of 6,607 milliliters per minute. All right, so let's refill everything, get everything back to baseline. It's going to ask us a question. Increase the right flow to radius. So what will happen to resistance and flow rate? Well, remember, we should see if we increase the radius, we're going to increase flow rate, but resistance should decrease. So predict, so if we increase the radius, what's going to happen to the pump rate? Okay, so if we increase radius, we decrease resistance. So we're going to see, and we should see an increase in heart rate or pump rate. All right, so let's see if that's what happens. Okay, so it wants us to increase the diameter. So we're going to increase flow rate. We're going to decrease resistance. So we're going to auto pump that. And again, this is what we should see. Stroke volume is 70. We're pumping 10 times. Remember, it told us to do 10 auto pumps. So this volume is going to be 770 strokes times 10 strokes gives us 700. Remember the first one, we did one single one and we left that 70 in. We didn't refill it. That's why you'll recall that it did say 770. So anyway, let's come down here. We're going to record our data. Again, stroke volume and pressure are going to be constant. What we did was increase radius, thus decreasing the resistance. If we decrease resistance, we have to increase heart rate. Okay, so we see heart rate go up in order to maintain blood pressure differences. And if we increase the amount of strokes per minute, we multiply that by how many strokes, that's going to give us how much cardiac output or blood flow. Okay, so we're going to refill. So anyway, I don't think any of this is surprising, but I did want to go through these and explain them in a little more detail. Left flow tube, pulmonary veins, left beaker, we said it was blood coming from the lungs, of course. Okay, so now it's going to have us increase by 0.5 until we get up to 5. So we're going to do this 3 more times. So auto pump. And again, this should end up at 700. We're going to record the data. And again, we see that we increased the radius, decrease in resistance. That decrease in resistance triggers an increase in heart rate. Okay, so we're going to bump that up to 4.5, auto pump, 10 auto pumps, record data. Again, we continue to see heart rate go up and therefore flow or cardiac output go up. Because remember, flow equals cardiac output, and cardiac output is heart rate times stroke volume. All right, lastly, we're going to do 5 millimeters for flow tube radius or the aorta. We're going to record the data, and voila, we have increased our radius, thus decreasing our resistance. That decrease in resistance led to an increase in heart rate in order to maintain our blood pressure. So, and stroke volume remained constant as well at 70 milliliters for every stroke or ventricular contraction. So that, I believe, is it. Asks us to plot the data. So you're going to plot the data, and again, we could see that nice, fairly linear looking plot. Okay, so we see roughly as we go up every half of a millimeter in radius, we see a similar increase in flow rate. Okay, well, I hope you learned a little bit, and when you perform these on your own, it does make a little bit more sense to you. So again, you want to get to the review questions, answer all of those. Looks like there are only 3. And then again, you're going to want to go down and click print, and it'll ask you to enter your name, printable version. Enter your name. Okay. Hit print. Save as PDF. Click save. Done. And then you've got another PhysioEx complete, and only a couple more activities left in exercise 5. So stay tuned. I'll be recording and uploading those soon.